Hello students, today's lecture is on plated beam. First of all, we will discuss on why plated beam. This is a simple problem. Before discussing on the problem, we'll say that these plates are provided in the top and bottom flanges. Why? Because when the loading coming on the beam cannot support the cannot be supported by a single ISM. Why this higher loading is coming? Because of large span or due to some higher load of high speed vehicles, of different types of trailers, trains, etc. So these plates are provided. Why we will provide the plate instead of going to a higher section? Because sometimes, like this problem, we have a span of 10 meter and have a load, but the available section is in the site is ISMB 500. So we have to utilize this section. So what we have done here, we have calculated the bending moment and shear force, factored bending moment and shear force for the coming on the section due to external load. Then we have tried to assume a section. While assuming the section, we have used this assumption that the section is plastic with no high shear problem, and we have used this basic formula of beam bending, which is provided in clause 8.2.1.2 in IS 800 page 53. So from here we have got the ZP required, which is 1422.8 millimeter cube or centimeter cube, say, and the available section at the site is ISMB 500, but the capacity or the plastic section modulus of that section is 2074.67 centimeter cube, which we have obtained from Annex H, page 138 of IS 800/2007. We can see that the required Z is much more higher than this provided Z. So what we can do, we can increase the capacity of the section by providing two plates at top and bottom, which will give you more as plastic section modulus and will also increase the moment of inertia. So first of all, what we have done, we have noted the sectional property of the ISMB 500 from our Annex H and SP6. What we have taken, the breadth of the flange, thickness of the flange, breadth of the wave, thickness of the wave and the IX6. So what we have tried to provide a plate of 280 millimeter thickness at the top and bottom, and we want to find out the thickness. We have to calculate the thickness required. From where we have chosen this 280 width? If we have a breadth of flange is which is 180, we have provided 100 millimeter bearing at both the side, projection at both the side. So 100 plus 200 will give us 380. 180 plus 200 will give us 380. So we have calculated from the basic formula the section modulus A by 2 YC plus YT. A is 2 into 280 into T divided by 2, 250 plus 250. This distance is 250. So we have also calculated the additional section modulus required. This is the required section modulus, and this is what is provided already by ISMB 500. We have subtracted this. So additional requirement is 2048.13. So which will be provided by this, and we have put this in equation to find out the thickness required to provide this amount of ZP. So we have found that the T required is 10.77, and we have tried with 12 millimeter thick plate. Now we have calculated the ZP. This is the ZP for the beam, and the additional ZP required provided by the 380 thick width of plate with 12 millimeter thickness. What we have done, area by 2 into this divided by 2 plus 256. Now the question is, why it is 256? Because now the distance is becoming 256, because we have to calculate it from the center. Then why we have considered in the previous case this as 250? Because the thickness data was not available at that time with us, so we have approximated it like this. Now when it is available, we have extended it up to the center. So now we have gone for the check of the class of section, where from we have calculated firstly the D, small d, the depth of the wave, which is the overall depth capital D minus 2 into thickness of the flange, which is 17.2 millimeter, and we have found it as 465.6. We have calculated BF by B by TF average. What is TF average? The average thickness of this plate. Sorry, the flange. So it is the 280 into 12, that is area of the top flange plate, and the area of the flange divided by the width of the plate and the width of the flange. We have got it as 31.03, and this ratio was calculated to be 6.12, which is less than 9.4 epsilon, and D by TW is also less than 84 epsilon. So we have concluded it as a plastic section. Nextly, we have gone for check for shear, where check for shear is calculated from clause 5.4, page 59, where first of all we have checked the ratio D by TW again, which is less than 67 epsilon, and hence we have concluded that shear buckling will not occur. Why shear buckling will not occur? If the slenderness ratio is less than 67 epsilon, it will not cause any shear buckling. If what will happen if shear buckling will occur, that will discussed on the next chapter or in some consecutive chapter of plate girder analysis or design. Now, if it is within this limit, Vn, the nominal shear, will be equal to Vp, the plastic shear. So this is Vp. AV is the area of the wave, D into TW, and FYW is 250, and it should be divided by √3 for shear factor, and we have calculated this as 686.47 and divided it with factor of safety. We got it for design shear Vd, which is greater than the shear coming on the section, hence it is safe against shear. Then we gone for the high shear check, which is 0.6 Vd, and it is coming marginally equal with this. So we have said that it is not causing any high shear, but in some cases, if it is strictly prohibited to cross any such marginal limit also, we may provide some wave plates near the support where the shear stress is higher. Why we are checking it for wave? Because the wave is taking the most of the part of the shear stress that we have discussed in the previous day's class of laterally supported beam. Lastly, we have checked it for bending with the formula which is provided in page 53, and we got that the beam is safe against bending. We are not going into the detail because we have used this formula several times. Lastly, we have checked it for deflection. We have seen that deflection coming on the section is 54.44. This formula is not given in the code. It is common formula that we have obtained from different deflection calculation process of conjugate beam method or moment area method, something like that. It is coming 54.44, and the delta max is L by 300, which is given in table 2. This is given in table 2 of IS 800-2007 is coming as 33.33. Now the thing is, the permissible deflection is lesser than the actual deflection coming on the section. That means it is failing due to deflection. So some solution is given at the end. If we want to save the section against deflection, what we can do? We can provide higher thickness of plate at the top of the and the bottom of the flanges, maybe of 16 millimeter thickness, 20 millimeter thickness, etc. Or to provide some secondary beam at the mid of the section required. That if the beam is having a span like this, we provide a secondary beam at the center. It will reduce the span of the beam, and the deflection will come down, because if the I is increased by providing higher thickness, this will be multiplied in the denominator, will reduce the thickness, deflection, and if the span is reduced, it is in the ordinate, so it will also reduce the it is on the numerator, it will also reduce the deflection. So this is the calculation method how we can do the design of plated beam. Thank you for patient hearing.